Hello everyone, I am Ruchi and I am a PhD scholar at Signal Processing and Communication Research Center at IIIT Hyderabad in India. In this video, I'll be presenting my paper titled Parametric Models for DOA Trajectory Localization. I have done this work under the supervision of my research advisor Dr. Santosh Nannuru. The ability to focus on the desired sound source within a noisy environment is a challenging task and has many applications such as smart homes, robots, cars, etc. The figure shown in the left is of two moving sources whose directional information is changing over time. In trajectory localization problem, we estimate the changing directional information of the moving sources. The challenges include interference from other sources, changing number of active sources over time, and the additive noise. In sound source localization, the aim is to find the direction of arrivals. Let us consider an n-element uniform linear array, where the spacing between two consecutive sensors is d. Under the far-field assumption, the wavefronts coming from sources are considered as plane wave, the direction from which the propagating vector is impinging on the microphone array is known as the direction of arrival or DOA. Let there be k sources and then the signal model for received signal on ULA is given by model 1, where y is the received signal, a is steering vector matrix whose columns are steering vectors corresponding to the k directions, x denotes amplitude of source signals, and n is the additive noise. When we have multiple measurement vectors at different time instances, we can write multiple snapshot model as equation 2. In block level processing, each L snapshot block is used to estimate the fixed DOA parameters. Model 2 represents static DOA model as DOA information is assumed to be fixed within the block. Both model 1 and 2 are narrowband signal models. In earlier slide, the static DOA model is shown, but in most practical scenarios, the sources are moving and the unchanging DOA assumption no longer holds. As a first order correction to this, we propose linear DOA trajectory model, where DOAs are changing across snapshots within a block. Linearly changing DOA, which is theta L as a function of snapshot L, can be captured using a two-parameter model as equation 3. Here, phi is the DOA in first snapshot and phi plus alpha is the DOA in the last snapshot of an L snapshot block. That is, the DOA changes by alpha by L minus 1 across each snapshot. The parameter pair phi comma alpha captures DOA motion within a block. Let us define A tilde phi comma alpha to be the matrix of all steering vectors as the DOA changes within linear model parameters. The multiple measurement model accounting for linear DOA motion is given by 4. Equation 4 is the MMV model which accounts for linear DOA motion. In linear trajectory localization, our goal is to estimate the parameters theta k, alpha k for all the sources and hence obtain their linear trajectory estimates within a block. In this work, we demonstrate the idea of trajectory localization by focusing on linear trajectories. However, it is straightforward to extend the linear motion assumption in 3 to higher order polynomials or other parametric trajectories. Here, we derive a modification of the conventional beamforming CBF algorithm for the proposed signal model. We refer to it as trajectory localization based CBF, that is TLCBF. In CBF, the angular power spectrum is computed at a predefined grid by evaluating the correlation between the observation and the steering vectors. The peak of this angular power spectrum provides DO estimates. Extending this notion, the TLCBF power spectrum for L snapshot is computed for every steering vector given by the formula here. Remember that each steering vector is now incorporating the information about potentially changing DOA within the block. Here we have formulated observations using a sparse model and later derived the compressive sensing based algorithm. For sparse formulation, consider a sample grid phi comma alpha. Let the uniformly sampled points in this rectangular space be denoted as phi 1 comma alpha 1 up to phi m1 comma alpha m2. A sparse model is given as equation 5. Here, A tilde and X tilde are changing DOA steering vector matrix and source amplitude matrix for the source located at phi m1, alpha m2. For enforcing sparsity on x tilde, we consider that only k sources are present in each block among all the potential m1, m2 sources. Remember, m1, m2 is much larger than k, which is number of sources. Here we assume that the true source lie on the grid. The above MMV model can equivalently written as a single measurement SMV model by vectorizing the observation matrix Y and appropriately changing the terms on the right hand side. Performing a column-wise vectorization operation on Y, we get model 6. Now the sparsity structure of matrix X tilde is translated into block sparse structure of the vector X tilde V. Once the previous sparse model is formulated, we derive CS-based algorithm of sparse Bayesian learning. We call this as TLSBL. For TLSBL, we assume that source amplitude are IID across snapshots and having zero mean complex Gaussian distribution. Here, gamma m is the source variance. In this slide, we use a simplified notation where double index m1, m2 is replaced by a single index m, and correspondingly the indices 1, 1 to m1, m2 are renumbered as 1, 2 up to m1, m2. We additionally assume that the amplitudes are independent across sources. Thus, the unknown x tilde v is Gaussian distributed and parametrized by the gamma vector. The noise is also a zero mean complex Gaussian distributed and IID across sensors and snapshots. Here, sigma square is the noise variance. In sparse Bayesian learning, gamma is estimated using evidence maximization. Since both prior and likelihood are Gaussian, from the properties of Gaussian densities, we get evidence to be Gaussian with zero mean and let the covariance being sigma yv. The TLSBL update rule is obtained by differentiating the log evidence with respect to gamma m. Due to the hierarchical probabilistic modeling of sparse Bayesian learning, the parameter vector gamma is sparse. This sparsity in gamma is reflected as block sparsity in the source amplitude vector x tilde v. Thus, the location of non-zero entries of gamma signify the source DOA trajectories estimates. In the results section, we demonstrate localization ability of the proposed algorithms using the simulations. Here we consider 4 off-grid sources, that is, the true sources do not lie on the predefined grid. The power spectrum obtained from various localization algorithms are shown in this plot. The true phi, alpha parameters are minus 15.5, 2.5, minus 25.5, minus 6.5, 47.5, 4.5, and 71.5, minus 12.5 in a 100 snapshot block. That is, now the DOAs are changing linearly. The top row shows power spectrum obtained from TLCBF and TLSBL, and the bottom row shows the power spectrum from conventional CBF and SBL. For TLCBF and TLSBL methods, phi, alpha pairs are estimated for each sources, whereas the traditional CBF and SBL, a single static DOA theta is estimated. The ground truth of the traditional algorithm is the average theta within a block. We can see that SBL and TLSBL can identify the off-grid sources well, whereas CBF and TLCBF miss a source. The corresponding DOA trajectories obtained from previous spectrum are shown here. The TLCBF and TLSBL algorithm can find accurate on-grid approximation of the true off-grid trajectories. Here we simulate a moving source with nonlinear DOA trajectory as shown. The trajectory contains 31 non-overlapping blocks of L equals to 50 snapshots each. Within each block, the DOA trajectory is approximately linear. The maximum change in DOA within any block is considered as 11.5 degree. Clearly, we can see that trajectories estimated from TLCBF and TLSBL closely align with true trajectory, whereas CBF and SBL provide fixed DOA estimate in each block. We also perform trajectory localization of two moving sources with nonlinear DOA trajectories as shown here. We consider 52 blocks with 30 snapshots each. The estimated DOAs by TL methods provide relatively smoother trajectories. The root mean square error for non-crossing regions are 2.98 degree, 3 degree, 2 degree and 1.78 degree for CBF, TLCBF, SBL and TLSBL respectively. So in this work, we introduced a signal model for identifying linear changing DOA for multiple snapshot block level processing. We developed the algorithms TLCBF and TLSBL for the estimation of linear DOA trajectories. The analysis can be easily extended to nonlinear parametric models. Though TLCBF can estimate changing DOA, it still has the drawback of low angular resolution inherited from CBF, which affects its performance in presence of multiple sources. The results show that TLSBL improves over sparse spatial learning by providing estimates of changing DOA while simultaneously having high resolution associated with compressive sensing based methods. Thank you for your time. For more details, feel free to join us in the poster presentation. Thank you.